The briefing begins now. Your mission is critical and far transcends standard data analysis. We are tasked with modeling the unseen enemy. This is not a simulation. This is a real-world conflict against an adversary of immense complexity, characterized by high-dimensional probability distributions. The objective is profound. We must understand the fundamental rules and patterns that govern the creation of all enemy assets. These assets range from high-resolution satellite imagery of terrain, as seen on the left, to highly complex data forms like encrypted communications and sophisticated financial transactions. Our ultimate goal is to reverse engineer this generative process and then build autonomous models capable of generating new, indistinguishable assets of our own. These generated assets must be so realistic that they are statistically identical to the observed enemy data. The key concept defining our operation is generative modeling. It is the branch of machine learning that focuses entirely on training a model to produce entirely new data samples that are fundamentally similar in structure and distribution to the given training dataset. On the left, you see the p-true, the true distribution of observed assets, and on the right, you see a sample from p-model, the generated asset. Notice the fidelity and complexity we aim to achieve. The difference between the two should be 0. Before we proceed, we must clearly differentiate our task. Our mission is fundamentally one of generation, not discrimination. Most machine learning operations currently deployed are discriminative. A discriminative model is trained simply to make a binary judgment or classification on existing data. Its objective is to estimate py given x, the probability of a label y given an observation x. A mission example would be training a model to predict if a given intelligence document is authentic, y equals 1, or a forgery, y equals 0. The model learns the features of authenticity but cannot create a new document. Its output is a label, not new data. Its purpose is merely to classify existing information. Our mission, however, is fundamentally different and far more difficult. We are not merely identifying the enemy's work. We are learning to replicate it from scratch. This is generative modeling. The objective is to estimate px, the probability of observing x itself, the entire data point, without reference to a specific label. The mission example for us is to train a model on a dataset of authentic enemy documents to understand their deep, underlying structure and syntax. Once the structure is captured, we then sample from this p-model to generate entirely new, plausible, and structurally sound intelligence documents that are indistinguishable from the true source. This shift from judgment to creation represents a significant tactical and technological leap forward. It is critical to understand the current state of the technological landscape. The front is rapidly advancing, and we must move quickly to stay ahead. Until very recently, the idea that a machine could successfully rival human creativity in generating complex high-dimensional data, such as realistic images, was generally dismissed as an unconquerable domain. That previous assumption is now obsolete, and we must discard it immediately. Generative technology is maturing at an exponential rate, characterized by tangible, stunning breakthroughs occurring year after year across multiple domains including visual data, audio synthesis, and text creation. This is no longer a theoretical exercise confined to academic laboratories. It is a deployable capability. The timeline visible on the screen demonstrates this accelerating capability, specifically in facial image generation. In 2014, outputs were low-resolution, blocky, and clearly artificial, failing basic authenticity tests. By 2016, we saw basic fidelity but clear imperfections and visual artifacts introduced by the generation process. The 2018 output achieved significantly high quality, though subtle flaws and asymmetries still remained visible upon close inspection. And now, in the present day, we are consistently seeing photorealistic, high-definition outputs that defy simple human detection. The rapid closing of this gap confirms that the core challenge of modeling complex, high-dimensional probability distributions is being successfully solved, demanding our immediate attention and investment in this area. Before we deploy to the main front, we will run a necessary tactical simulation in 2 dimensions to ground our understanding of the generative objective. The graphic depicts a map of the world. The black points scattered across this map represent observed enemy positions, or data samples. These samples were generated by an unknown, underlying mechanism that dictates where enemy assets can plausibly exist. This underlying mechanism is the true data-generating distribution, which we designate as P-true. P-true in this case is the actual shape of the landmasses that hold the positions. Our ultimate task is to define a model, which we call P-model, that can effectively and mathematically approximate this underlying rule, capturing the exact structure of the continents. The data samples exist in a two-dimensional sample space. Dimension 1, the x-axis, represents longitude, and dimension 2, the y-axis, represents latitude. The specific coordinates of the black points define the training data for our initial model. Our first attempt at defining P-model will illustrate the foundational challenges inherent in approximating any complex distribution, even one that appears as visually straightforward as a world map. Success in this simulation requires a P-model that assigns zero probability to the vast empty ocean areas, while correctly assigning high probability only to the observed landmasses. This slide presents the after-action report for our initial, simplistic attempt at defining P-model. For our first pass, we modeled P-model as a large, crude rectangular orange box, which is a significant oversimplification of the true distribution, P-true, which is represented by the gray landmass. Analyzing this failure and its few successes allows us to define the three absolutely critical properties that any effective generative model must possess for field deployment. First, we demand accuracy. Mathematically, high P-model X should accurately mean that the generated observation X looks exactly like it came from P-true. The area labeled A illustrates a major failure. The model assigned high probability to an empty ocean area, generating an observation that is clearly implausible. The area labeled C, however, represents a success, as it is a plausible sample found on land. Second, we must achieve generation. It is non-negotiable that we must be able to easily and efficiently sample new, novel observations from our P-model. If the process of sampling new data is computationally difficult or slow, the model is useless for deployment. Third, and perhaps most complex, is representation. The model must successfully capture the high-level, intrinsic features of the true data distribution. Failure B, incomplete generation, shows that our simple rectangle model completely missed entire continents and major land features, failing to represent the true, complex distribution structure. An effective, deployable generative model must simultaneously satisfy high accuracy, easy generation, and detailed feature representation. Directly modeling the immense complexity of high-dimensional space, such as a large image composed of millions of pixels, is inefficient, computationally crippling, and extremely brittle. The superior strategic approach, which we must adopt for operational success, is called representation learning. This strategy involves mapping our complex high-dimensional assets, like equipment schematics, into a significantly simpler, low-dimensional latent space. The critical factor is that every dimension within this simplified latent space must correspond to a meaningful, high-level feature of the asset. For example, a dimension might correlate directly to vehicle size, or weapon payload capacity, or effective operational range. By operating exclusively within this simple latent space, we gain critical advantages, primarily the ability to control and generate new assets with surgical precision. The process involves two primary components. First, the encoder takes the high-dimensional samples on the left and compresses them into a specific point or vector in the low-dimensional latent space. This step is mapping the complex data to a simplified chart. Second, the decoder, or the mapping function G, handles the complex, inverse task. The key insight here is that manipulating a vector in the low-dimensional latent space, for instance, by linearly increasing the effective range dimension, is trivial. The decoder then translates that simple vector manipulation into the necessary, highly complex rendering changes in the high-dimensional image, resulting in the new generated asset. This mandatory briefing covers the critical language of the battlefield. Mastery of the following technical terms is non-negotiable, as this is the precise language we use to define, measure, and engage the enemy. Commit these terms to memory. First, the sample space is the complete set of all possible observations, denoted as X in our training simulation, This was every single coordinate point on the map, both land and sea. Second, the probability density function, or PDF, is a mathematical function px representing the relative likelihood of any single observation. Our primary mission objective remains building a p-model x that accurately mimics the unknown p-true x third. Parametric modeling is the strategy of constraining our complex model to a family of functions that are fully described by a finite set of parameters, denoted as theta. This limitation is essential for tractability. For example, for a simple rectangular model, the parameter set theta would only contain x minimum, y minimum, x maximum, and y maximum, fully defining the rectangle. Fourth is likelihood, L theta given x. This measure quantifies the plausibility of a specific parameter set theta. Given an observation x, it is defined simply as px semicolon theta. For an entire dataset x, the total likelihood is the multiplicative product of all individual likelihoods. Because multiplying many small probabilities leads to computational underflow, we commonly use the log likelihood instead for crucial computational stability, which transforms the products into safe summations. Finally, the core technique for model training is maximum likelihood estimation, or MLE. We are seeking to find the optimal parameter set, theta hat, that maximizes the likelihood of observing our entire training data. This process is mathematically equivalent to the process of minimizing the negative log likelihood, which is the standard optimization mechanism by which all neural networks in this domain are typically trained to convergence. We have successfully established our primary objective, maximum likelihood estimation, and we have mastered our language probability theory. Now we face the central conflict, the fundamental obstacle of intractability in high dimensions. This issue is often referred to as the Curse of Dimensionality, and it affects all generative tasks. For any problem involving meaningful real-world complexity, such as high-resolution images, complex audio, or natural language text, the true probability density function px semicolon theta is mathematically intractable. This means we cannot calculate it directly in any reasonable timeframe. The primary reason for this operational failure is the astronomically vast sample space. Consider the explanation: a simple 256 by 256 grayscale image. The total number of possible images in this space is 256 raised to the power of 65,536. To put that scale into perspective, this number is exponentially greater than the estimated total number of atoms in the known universe. It is an incomprehensibly large space. Furthermore, the set of valid or plausible images, those that actually look like real-world objects and terrain, occupies an infinitesimally small manifold, a tiny subspace, within this immense sample space. Finding and modeling this minuscule manifold is the true difficulty. The mission challenge, therefore, is crystal clear and seems insurmountable. Directly maximizing a likelihood function that we cannot possibly compute is impossible. We must abandon direct MLE and find alternative combat doctrines that circumvent this intractability. The immediate problem of intractability has forced the rapid evolution of diverse combat doctrines in the generative field. This slide presents a vital battlefield survey, offering a taxonomy that classifies all generative models by how they choose to confront this central computational challenge. It is essential to understand this landscape before deployment. All models fall into one of two major classifications. The primary division is between strategies that model the density function explicitly, meaning they write down a formula for it, and those that model it implicitly, meaning they generate samples without ever writing down the formula. First, we have explicit density models. These are models where we define and work directly with a p-model x function. These are further divided based on how they handle the computational difficulty. We have tractable density models, where the PDF is deliberately designed through architectural constraints to be computationally computable, allowing for exact likelihood calculation. The second subgroup is approximate density models, where we concede that the full PDF is too complex, and instead we use a simpler, tractable approximation of the true PDF, often by using a proxy objective. On the other side are implicit density models. These doctrines fundamentally abandon the attempt to define or approximate the density function altogether. Instead, they create a stochastic process, a series of steps, that samples directly from P-model X without ever needing to define the function itself. They generate the data first, and the density estimation is then secondary or irrelevant. Doctrine 1 is the direct assault via tractable density. These models confront the intractability problem head-on by imposing very strict, powerful architectural constraints. This forcing mechanism ensures that the resultant probability density function is always in a form that is computationally tractable, allowing for direct, exact likelihood calculation and maximization. The first unit profile under this doctrine is autoregressive models. Their tactic is sequential generation. They systematically decompose the joint probability of all features, whether those are pixels in an image or words in a sentence, into a strict product of conditional probabilities. The model then generates one feature at a time, strictly conditioned on all the features that immediately preceded it. The analogy for this is assembling a complex device one component at a time, meticulously following a strict instruction manual, ensuring every piece fits perfectly. This approach is highly methodical and exceptionally precise, guaranteeing high accuracy, but the inherent sequential nature means that the generation process can often be prohibitively slow, making parallel generation extremely difficult, especially for high-resolution images. The second unit profile is normalizing flows. Their tactic is transformative generation. They start with a simple, known, and easily computable distribution, such as a standard Gaussian distribution. They then apply a series of invertible, one-to-one, and computationally tractable functions, also known as flows, to systematically warp that initial simple distribution into the complex target distribution. The key is that because the transformation is invertible and differentiable, the probability density can be calculated exactly by tracking the warping through the entire chain of transformations. The analogy for this method is taking a standard, uniform block of raw material and using a precise series of reversible tools to sculpt it into the final, highly complex shape required. Doctrine 2, battlefield mapping via approximate density, represents a crucial shift in strategic thinking. This family of models concedes that the true density is definitively intractable and cannot be solved for directly. Instead of solving for P-true directly, they define and optimize a simpler, computationally tractable approximation of the density function. The core strategy utilized here involves the principle of variational inference. The key unit profile under this doctrine is the variational autoencoder, or VAE. The VAE's fundamental tactic is to introduce a latent variable, z, to represent the high-dimensional data, x, in a significantly simpler, lower-dimensional space, which we call the latent space. A VAE consists of two distinct, interacting neural networks. First, the encoder, often referred to as the recon unit, approximates PZ given X. Its mission is to map the complex, noisy terrain of the input data down to a simplified chart in the latent space, effectively compressing the information. Second, the decoder, or the fabrication unit, models PX given Z. Its role is to use that simplified, structured chart to successfully generate new assets, mapping the latent variable back to the high-dimensional space. The objective of the VAE is central to this doctrine, because directly maximizing the mathematically intractable data likelihood is impossible. We instead maximize a tractable lower bound on it. This lower bound, known as the evidence lower bound, or ELBO, acts as a measurable, operational proxy, objective for successful learning and accurate generative modeling. Continuing with Doctrine 2, we must cover advanced approximation tactics that exist beyond the standard variational methods to approximate the target distribution. These offer different ways of approaching the intractable PDF. The first unit profile is energy-based models, or EBMs. The core tactic here is to define an energy function. This specialized function assigns a very low energy value to authentic data points, which are desirable samples, and assigns a very high energy value to inauthentic or nonsensical points, thus defining the distribution implicitly through energy landscape. The probability of any data point is then defined as proportional to the inverse of this unnormalized energy function. Training and sampling from EBMs are computationally very challenging, often requiring complex, specialized processes like Markov chain Monte Carlo or MCMC methods to navigate the energy landscape. The analogy is probing an enemy's force field to find specific weak points, the points of low energy, rather than attempting the impossible task of mapping the entire complex field structure. The second, and currently most impactful, unit profile is diffusion models. Their tactic involves a crucial two-stage temporal process. In the first stage, the forward process, we systematically destroy the structure present in the training data by gradually adding Gaussian noise over many discrete time steps until the image is reduced to pure, random noise. In the second stage, the reverse process, we train a neural network to perfectly reverse this systematic degradation process. The network learns to meticulously denoise the data step by step, estimating the exact amount of noise to remove at each time point. Generation then starts from pure noise and applies the highly learned denoising process iteratively to generate a coherent, high-fidelity sample. The analogy for diffusion models is deconstructing a captured enemy weapon down to its basic components to learn exactly how it functions, and then using that perfect knowledge to build an entirely new, structurally sound weapon from scratch. Doctrine 3, subterfuge via implicit density, is a radical shift in strategy and perhaps the most complex to train and stabilize. This doctrine fundamentally abandons any attempt to define or analytically approximate the mathematical density function. Px, the sole focus here, is on creating a robust, stochastic process that can directly generate data samples that appear to be drawn directly from the true distribution. The key unit profile here is generative adversarial networks, or GANs. The core tactic is structured as an adversarial, non-zero-sum, two-player game played between two competing neural networks that are trained simultaneously. The first player is the generator, or the forger. The generator takes random noise as its input, which serves as the latent variable, and attempts to transform it into plausible synthetic data. The second player is the discriminator, or the analyst. The discriminator is presented with synthetic data from the generator and real data from the source, and its mission is to correctly classify which asset is real and which is a forgery. The conflict is the defining characteristic of this doctrine. The generator's sole goal is to successfully fool the discriminator every time, striving to maximize the discriminator's error rate. Simultaneously, the discriminator's goal is to not be fooled, striving to minimize its error rate. They are trained simultaneously in a continuous feedback loop, receiving real or fake feedback. Over time, the forger becomes so proficient at creation that its outputs become statistically and visually indistinguishable from the authentic assets. Crucially, by achieving this perfect deception, the generator implicitly captures the structure and complexity of the true data distribution without ever having to define it mathematically, thus circumventing the intractability problem through competition. While the specific strategies, tactics, and doctrines we have reviewed vary widely, a common, powerful thread runs through all modern, sophisticated generative models. They are all fundamentally powered by the same unifying force: deep neural networks. It is the architectural complexity, the massive parameter count, and the capacity of these networks that makes all these recent advancements possible, regardless of whether the model uses explicit or implicit density. We must understand why the use of deep neural networks matters so much to our mission. The first critical advantage is automatic feature learning. Neural networks possess the unique capacity to learn the highly complex, hierarchical relationships that govern the intrinsic structure of the data automatically, without any manual intervention. This eliminates the requirement for human engineers to painstakingly hardcode domain-specific information or perform feature engineering. The network autonomously discovers the relevant patterns. The second advantage is scalability. Deep neural networks can scale effectively and efficiently to handle the massive dimensionality inherent in real-world data assets, such as high-resolution images, complex audio streams, and immense volumes of text that define our adversary. Without this necessary capacity for scale, none of these generative models would be deployable in the field. The third crucial benefit is flexibility. The underlying architecture of a deep neural network is highly flexible, making it adaptable enough to be integrated into the mechanical framework of any of the diverse doctrines we have reviewed today. We can adapt a DNN to handle the strict sequential generation requirement of autoregressive models, implement it within the two-player game structure of GANs, or use it to define the invertible transformations necessary for normalizing flows. This inherent flexibility ensures our tools remain relevant across the entire generative spectrum. Our final objective, the ultimate goal of this research, extends far beyond simply generating enemy assets. The success achieved in generative modeling is now driving monumental progress across other domains of artificial intelligence, most notably in areas like reinforcement learning. Here, generative models are used to create highly accurate world models for AI agents to train in, allowing them to simulate reality and learn complex tasks faster than real-time, dramatically accelerating mission readiness. However, the most profound implication for our strategic mission comes from the field of neuroscience. Current leading theories suggest a radical reevaluation of human sensory processing. They propose that the human brain is not merely a discriminative machine passively processing incoming sensory input by classifying data. Instead, it operates as an incredibly powerful, internal generative model. This model constantly produces predictive, high-fidelity simulations of our surroundings that are continuously matched and updated against incoming sensory data. Therefore, what we consciously perceive as objective reality may in fact be the sophisticated output of this internal generative model, our brain's best approximation of P-true. Our mission, therefore, is not merely to build machines that can generate data. It is to fundamentally understand the mechanisms of prediction, imagination, and intelligence itself, solving the riddle of creation. The campaign continues.